And we're back. This is Mr. Robeson here. We are looking at the power of a hypothesis test and some examples of how power is used. So power is a pretty useful thing. And honestly, if you're doing any sort of test in any sort of actual field, you do want to know what is the power of your test. Like, it's how good is your test at telling you what you want to know. So the power of the test is the probability that the test will find convincing evidence for the alternative hypothesis when a specific alternative value of the parameter is true. All right, so in other words, we have some other value, not our null hypothesis, for either the mean or the proportion, the true proportion or the true mean. We know that it's going to be something else in the end from what we thought it was going to be in the beginning. All right, and we see, well, how good was our test based on that other actual value? So the power of the test is the conditional probability of rejecting the HO given that the mean equals some specific alternative value. So it's a probability that we reject the HO given that the alternative is actually true for some specific value of it. All right, some of you are probably like, uh-oh, he's using probability notation again. We don't remember that from Unit 4. It's okay. It's okay. All right, so there is a formula for the power of a test that you don't need to know, but it does involve areas of normal curves. All right, we can show how to actually get it. That's what we need to know, is how to get it. We don't need to try and memorize the formula. It's kind of long. All right, but we do need to know that the power and the probability of a type 2 error are related to each other. Like, those two things add up to 1. All right, because so either you've got your test is doing the right thing or your test is doing the wrong thing, but those two things add up to 1. All right, so just remember that the power is equal to 1 minus the probability of type 2 error, or the probability of type 2 error is 1 minus the power, or just remember that the power plus the probability of a type 2 error is equal to 1. All right, so there's a couple things we can do to increase the power of the test, to make our test stronger, in other words. One of them is a larger sample size. That makes the power go up. Another one is we can have a larger level of significance. That will also make our power go up. And if the null hypothesis and the alternative parameter are farther apart, like if we find out that the mean is actually farther away than from the null hypothesis, or the true proportion is farther away from the null hypothesis proportion, that also makes our power go up. All right, so let's just start with some basic stuff. I know this is going to be a little confusing, but we'll see what we can do. It shows up on the AP exam about every third year, so it's not a huge deal if you struggle with this. So recall the AAA battery example. The population mean life was 30 hours. They selected 50 new batteries and tested to see if it lasted significantly longer than the original batteries. Suppose the power of the test to detect that the true mean is actually 31 hours for the new batteries is that. So this is our power. Interpret this value. So what this means, if the true mean life of the batteries is 31 hours, and we do a hypothesis test, thinking the mean was 30 hours, again, that was our null hypothesis, then there is a probability of correctly rejecting the null hypothesis that the mean equals 30 hours of 0.762 or 76.2%. So there's a 76.2% chance that our test is going to tell us to reject. And it should tell us to reject because the mean is actually more than 30. The mean is actually 31. So it's not the 30 that they told us that it was in the beginning, or that we thought it was in the beginning. All right, so that's what power means. All right, so here's another way to write it. So if the true mean lifetime of the company's new batteries is 31 hours, there is a 0.762 probability that the company will find convincing evidence for the alternative hypothesis. In other words, we'll do the correct thing. That is, the probability of rejecting the null hypothesis when the true mean is 31 is 0.762. So that means the probability of making a type 2 error, as in not rejecting when we should have, is 0.231, 1 minus the power. All right, so a lot of things you can write about that. So where does that 0.762 come from in the battery example? That's tricky. So what ends up happening, and let's see, there's some graphs here too. So we start off thinking our mean is 30. In which case, if we are up here, and this is the alpha, 0.05, if we end up here, that's what we call the rejection region. This is where we'd end up rejecting. So the cutoff value for that is 30.69. So what we do is we say, okay, here's our normal curve with a mean at 30. And it's a sampling distribution, so the standard deviation for this sampling distribution would be 3 divided by the square root of 50. So this was the sample, there's the sample mean, sample size, there's alpha, and there's our standard deviation. The company knows this. This is sigma. All right, so population standard deviation. All right, so what we do is we have this distribution, and we want to know where's the cutoff. Where do we reject? Above what number do we reject? And below what number do we fail to reject? So this would be reject up here, because this is the size of this region is alpha, which is 0.05. Then this must be 0.95, and this would be what we call the fail to reject region. All right, so we need to know that cutoff. So what we do is we do the inverse norm of that 0.95 with a mean of 30 and a standard deviation of our sampling distribution. And that gives us 6979. So if we get anything bigger than that for our sample mean, we would end up rejecting. Okay? So now, if the true mean really is 31, what is the probability that a random sample of size 50 with standard deviation of 3 will be above that number that we just got? So then what we do is we take a look at another curve, and I don't want to draw it here because I know another one's going to pop up down there in just a second. But we take a look at the other curve, which is actually centered now at 31 with a standard deviation. So this is my mean, 31. This right here is going to be my standard deviation of that new distribution because their sample size is of 50. The population standard deviation was 3, so that was my sigma. And we want to know what's the probability of being above this number. So we just go from that number on up. And this right here is the power of the test, right? Because this is the actual distribution that we've got, because the actual mean is 31 and the actual standard deviation is 3, and we're doing a sampling distribution with samples of size 50 still. So this is what's actually there, not this guy. This guy is not the actual distribution. All right, so we end up looking at this. So here's my first curve again, right there. And then this is the second curve. That's this guy right here. All right? And this area ends up being 0.762, and that is the power. So this section right here is the power of the test. So most of the samples we get, 76% of them, would be here. But if we got one that was over here, that would be a type 2 error. All right, because if we got one over here, we'd still be pretty close to that mean that we thought it was before, that 30, and we wouldn't end up rejecting, even though the new mean is actually 31. All right, so that's what's going on with power. It's kind of a sneaky thing. All right, and before we go into that, I do just want to say some other things about this. So if alpha was bigger, so let me change colors here. So remember, we have a couple ways that this can be different. So if alpha ends up being bigger, like maybe 0.10, we add this section to it, which moves this line over to here and makes our power bigger. All right, so you see how that works? If alpha is bigger, the power also gets bigger. All right, another thing that can happen is if we change our n. So if our n gets bigger, this curve gets narrower and taller. It's kind of tough to draw. But that means then alpha would be farther over here because it'd be shorter, which again moves this over and gives us a larger region here for power getting bigger. All right, tough to draw here with my little pad. But that's, again, those are two of the things that can change it. The other thing would be if the actual mean was farther over. So if this mean, instead of being 31, was like 33, and then we had a curve distributed around here, then our power would be probably very close to 100%, because just being above here would be almost everything. All right, so now if the power of a test is determined to be 0.853, what is the probability of making a type 2 error? Well, power plus the probability of a type 2 error equals 1, because it's just the area under the normal curve. So this is 0.853. This is what we're trying to find. So it's just 1 minus 0.853. And I believe that works out to 147. So the probability of a type 2 error would be 14.7%. All right, another example. I think this is it. So if alpha is 0.10 for the AAA batteries and the standard deviation is still 3, sample size is still 50, the null mean is still 30, what is the power of the test if the alternative mean ends up being 31? What does that power mean? What is the probability of making a type 1 error? So we got 3 questions here. So first, what is the power? All right, so we've got our normal distribution. That one's pretty good drawn on my part. Here's our mean from our null hypothesis. So this is what we're thinking is happening with our null hypothesis. We've got a standard deviation of this sampling distribution of 3 over the square root of 50. Alpha is 10, so that means we've got 10% up here for our rejection region, which means this is 90% here for our non-rejection region. So to find this value right here, we do inverse norm of this area, 0.90, with a mean of 30 and a standard deviation of 3 over the square root of 50. And that's going to give us that cutoff, which I think is going to be slightly different than the last one, because the last one we did it with 5%. So second distribution, inverse norm, area is 0.90 or 0.9. Our mean is 30. Our standard deviation is 3 divided by the square root of 50, because we're taking samples of size 50. And this is a sampling distribution. And we get 30.54, 543, I guess, or 544, I guess that would round to. So we get that this is 30.544. That would be the sample mean where the rejection region would start, and everything above that we would reject. So now we come in and we say the actual mean is 31. So actually, we've got this curve up here with a mean at 31. The standard deviation is still going to be the same. We still have the same 3 over the square root of 50. And we want to know what's the probability that we are above this 30.544. So what's the probability of being over here? All right, because if we're up here, then we would be rejecting, and that would be the right thing to do, because this is the rejection region. All right, so we go back to our calculator, and we're going to do normal CDF with this. So second distribution, normal CDF, and we want to be above that 30.544, was it? I wrote it down. Yeah, 544, that'll work. All right, and we can just keep going up from there, something big. All right, our mean here is actually 31. Our standard deviation for our sampling distribution is 3 divided by the square root of 50 still. And let's see what that gives us. 0.8587. 0.8587. And that is the power of the test. And notice it has increased, right? And the only thing that changed was alpha. So alpha went from 0.05 to alpha equals 0.10. And that led to the power increasing. All right, it was 0.7, now it's 0.7 something, 0.762 was it, or 0.72? I don't remember what it was. But now it's 85 or 86%, so the power has gone up. All right, so now the probability of, so this is the probability of rejecting the null hypothesis that the mean is 30. I keep writing wrong. When the mean is really 31 is 0.8587. That is what this power means. What's the probability of making a type 1 error? Type 1 error. Think back. Remember we said the probability long ago is probability of a type 1 error is exactly alpha, 0.10. All right, so that would be rejecting the HO if the HO was true. That's what type 1 error. Probability of a type 2 error would be 1 minus this guy. All right, I was just throwing that in there as a curveball if you remembered that. All right, find the power of the test if one thinks the true mean is 52. So we've got a mean of 50, standard deviation of 5, a sample size of 40, and an alpha equals 10. So let's see, we've got one normal curve here that's going to be centered at 50. We're going to have another normal curve up here. I don't know, that's a bad drawing. Centered at 52. We've got somewhere, let's see, we've got mean, we've got a standard deviation of the sampling distribution, 5 over the square root of 40. And I'm assuming we're going to check a one-sided test and that our alpha will be here and that this will be 0.10. So this is 0.90, and we want to know what's this value. So we throw this into our calculator. We're doing inverse norm here. Second distribution, inverse norm. The area is 0.90. Oops, I did say t distribution. Hang on, I hit the wrong one. Second distribution, inverse norm. There we go, number 3. So 0.90. Our mean is 50. Our standard deviation is 5 divided by the square root of 40. And let's see what happens. We get 51.01. 51.01. All right, so it's probably actually a little closer to here, but these curves are probably a little closer to each other. All right, now we're saying, okay, what's the probability in this other curve of getting above 51? All right, well, it still has this same mean. It's still going to have the same standard deviation as far as we know. And we want to know what's above 51. All right, so we go back to our calculator and we do the just normal CDF with 51.01 as our lower bound, something big as our upper bound. All right, a mean of 52 and a standard deviation of 5 divided by the square root of 40. By the way, we did all these with mean because I think it's easier for you guys to picture mean. We could have just as well done all these with proportions too. So we get that this area is 0.895, I guess that would round to. 0.8947 and so on. So it looks like there it is. All right, so that was power. I know power is a little tricky. You can go back and look at it again. There's a small chance it'll show up on the AP exam, so don't worry too much about it. But if you can figure it out, good for you.